In our last class, we have been discussing about leptons, which are particles which undergo only weak interaction. Now we are going to discuss hadrons, which are particles which are subject to strong interaction. In hadrons, we have basically two types of particles, the mesons and the baryons. Mesons are made up of a quark and an antiquark. Baryons are made up of 3 quarks. The mesons usually discussed are pions and kaons. Pions consist of pi plus, its antiparticle is pi minus, pi 0, it itself is its antiparticle, pi minus, its antiparticle is pi plus, then kaons, k plus, k0, s, k0l and their corresponding antiparticles. Then you have eta particle, which is very short-lived particle. Then baryons. In baryons you have nucleons, which consists of protons and neutrons. Their corresponding antiparticles are antiproton and antineutron. Then lambda particle, which consists of lambda 0 and its antiparticle lambda 0 bar. Bar denotes the antiparticle. Then sigma. All these we have discussed in our classification. Sigma particle, sigma plus, sigma 0, sigma minus, their corresponding antiparticles. Z particle, Z0 and Z minus, their corresponding antiparticle. With a bar you designate the antiparticle. Then omega minus is the particle, baryon, and its antiparticle is omega plus. Then there are very short-lived particles. They are called resonance particles. If you observe the bombardment of a pion, pi plus meson is interacting with proton. In the interaction, 3 new pions are generated in this particular interaction. There will be pi plus, proton plus 3 new pions are created. If you look at this bombardment event, the number of events per 10 MeV interval. 10 MeV is the energy. So if you plot the number of events with respect to energy, you can see that when the counts are plotted, there is a peak about 549 MeV and 783 MeV. That means there are more number of particles in this region. That means in this energy and this energy. So, but finally you are getting this as the output product. So what it means is there are some particles, intermediate particles, which are being generated at this energy. They decay into the corresponding pions later on. These intermediate particles are having very small lifetime. We can call them eta particle and omega particle, or eta mesons and omega mesons. From this energy, you can find out what is the lifetime of those particles. This is a peak. You can find out width at half maxima. This will be half maxima. At half maxima, you can find out the width. From that width, you can find out mean lifetime tau as equal to h cross by gamma. Gamma is the width at half maxima. At this peak you take half maxima, you take the width of the half maxima, you substitute, and h cross by width of half maxima will give you the lifetime of that particular meson. So eta meson you get the life as 5 into 10 raised to minus 19 seconds, and omega meson you get as 7 into 10 raised to minus 5 seconds. So resonance particles are very short lifetime particles. So in a reaction, it may be going through different stages in which resonance particles are the particles generated in the intermediate stage, and finally they decay into the corresponding particles which we see after the reaction. These will be the stable particles. So unstable particles will be formed in the process. Now coming to the elementary particle quantum number. You are already familiar with the quantum numbers of an atom, of an electron. you have discussed the orbital quantum number, spin quantum number, magnetic quantum number, so many quantum numbers you have discussed in relation to an atom. Now we'll be discussing the quantum numbers related to an elementary particle. So first I'll list out what are the different quantum numbers to be discussed. One is the lepton number, L. Lepton number is designated by L. It is equal to 1 for all leptons and -1 for their corresponding antiparticles and 0 for those particles which are not leptons. This we have discussed in the previous class when we were discussing leptons. Similarly, baryon. For baryons, the baryon number is 1 and antibaryon, the baryon number is -1. That means for the antiparticle, baryon number is -1. For all other particles which are not baryons, the baryon number is 0. Then another quantum number is isospin, electric charge, strangeness, hypercharge. So these are the quantum numbers associated with the elementary particle. I'll discuss each of these. Lepton number we have already discussed. We have lepton number corresponding to electron, Le, lepton number corresponding to the tau particle, lepton number corresponding to the muon. All these we have discussed in the previous class. Similarly, baryon number corresponding to each baryon. If you look at the classification, in the baryons you have the nucleons and the hyperons. All of them have baryon number 1 and their antiparticles have baryon number -1. All the particles which are not baryon, when I say not baryon, they are either leptons or bosons. They will be having baryon number 0. Then coming to isospin. Isospin is actually the average charge of the members of a multiplet. There are different multiplet states. So the average charge will be represented by the isospin. Isospin I is equal to, you can represent I in such a manner that 2i plus 1 will be giving the multiplicity of that particular state. That means different states are possible. How many different states? If 2i plus 1 states are possible, we can call I as the isospin of that particular state. So for I equal to 0, the multiplicity will be 2 into 0 plus 1, that is equal to 1. So multiplicity is 1 when I equal to 0. So it is having only a singlet state. Only one particular state is possible. If I equal to half, 2 into half is 1 plus 1, 2. So two different states are there. So each of this, the component of I will be, you call it I3. So what are the different possible values? I3 can have plus half and minus half. Two different states are possible when I equal to half, and these corresponding values are plus half and minus half. When I equal to 1, the multiplicity is 2 into 1 plus 1, that is 3. So 3 different states are possible. The possible values of I3, that means components of I, in the any specified direction, you can correspondingly find out as I minus 1, 0, etc. up to minus I. So these are the different possible values of I3 you get. I3 is component of I in any specified direction. So next quantum number is electric charge. Electric charge E is equal to, how you get the electric charge Q is equal to, E is the charge of the electron, that into I3 plus B by 2 plus S by 2. B is baryon number. I3 is the component of I in the specified direction. B is baryon number. S is called strangeness. What is strangeness? I will tell you. So S is strangeness, and another quantity is hypercharge. Hypercharge is designated by the letter Y, that is equal to S plus B, where S is strangeness and B is baryon number. So we have mentioned that a baryon will consist of 3 quarks and a meson consists of a quark and an antiquark. So let us see what are the quarks. There are three different types of quarks, U, D and S. Both baryons and mesons are made up of these three different quarks. A baryon will consist of three quarks and a meson will consist of one quark and one anti-quark. If you look at a proton, the quark composition of a proton is UUD. That means there are two U quarks and one D quark. If you look at a neutron, it consists of UDD, one U quark and two D quarks. Now let us see the characteristics of this quarks U, D and S. Three different types of quarks U, D and S. Corresponding charges I have written. Charge of a U quark is plus 3 by 2e. Charge of D quark is minus 1 by 3e. Sorry, U quark plus 2 by 3e. D is minus 1 by 3e. S is minus 1 by 3e. And the spins of these quarks, they are spin half particles. Their baryon number. U quark has got a baryon number 1 by 3, D quark has a baryon number 1 by 3, S has got a baryon number 1 by 3. Then S is strangeness. U quark strangeness is 0, D quark strangeness is 0, S quark has a strangeness minus 1. Then isospin. Isospin of U quark is half, D quark is half, S quark is 0. So the component I3 corresponding to half is, for the U quark it is plus half, for the D quark I3 is minus half, and for the S quark I3 is 0. Now let us look at the composition of some hadrons according to the quark model. Hadrons consist of mesons and baryons. So let us look at a pi plus meson. A meson will consist of a quark and an anti-quark, a U quark, anti-D quark. Now let us look at the baryon number. You substitute the value for U, baryon number 1 by 3. For D baryon number is 1 by 3, anti-D quark baryon number will be minus 1 by 3. So 1 by 3 minus 1 by 3 is 0. That means pi plus meson is having baryon number 0. Definitely we should get baryon number 0 because meson is not a baryon. So here you get 0. Now look at charge. You can substitute for U. Charge of U is plus 2 by 3. D minus anti-D quark. D quark has got minus 1 by 3 charge. So anti-D will be having plus 1 by 3. So this will give you equal to 1. So it has got 1 unit of charge, that is 1 positive charge. So pi plus. And the spin. U quark has got a spin plus half. This is denoting the plus half. Plus half or minus half only designates the direction in which the spin is oriented. U quark spin half in the upward direction. Then D quark has a spin again in the upward direction, but here it is anti-D quark. So it will be in the opposite direction. So two spins in the opposite direction. So effective spin will be 0. So our pi plus meson becomes a spin 0 particle. Now look at strangeness. Strangeness S. U quark has got a strangeness 0. Anti-D quark also has got a strangeness 0. 0 plus 0 is 0. So you get the different parameters corresponding to a pi plus meson. Similarly, you can find out the various parameters for K plus. Then this is proton, this is neutron, omega minus particle. Corresponding quark composition, if you know, you can substitute the values of their corresponding quarks and find out the baryon number, charge, spin and strangeness. For K plus meson, the quark composition is U and anti-S. For a proton, UUD. For a neutron, DDU. For an omega minus particle, it is SSS. So this is the quark composition of some of the hadrons. Similarly, you can find out what are the different quantum numbers, baryon number, charge, spin, strangeness, etc. for other particles once you know the quark content of that particular particle.